So far we've talked about several different notation for permutations in SN. We have generator notation, matrix notation, one-line notation, two-line notation, and we've got pictures called wiring diagrams. There's another notation which is going to be very important for us and is very important for many reasons. It's called cycle notation. So let's look at the cycles in permutations. Let me start with an example. Let's look at the permutation whose generator notation is S3, S2, S3, S1. So the wiring diagram looks like this. S3, S2, S3, S1. Now if we were to wrap this around a cylinder, we would turn the wires into loops, which are called cycles. So in this case, we get, let's see, 1 goes to 2, and then it wraps around, and 2 goes to 4. We wrap around, 4 goes back to 1. So we've got this loop 1, 2, 4, 1, which we write in parentheses like this, and it's understood that the last letter here goes back to the first. We could also write this 2, 4, 1, or 4, 1, 2. And then 3 goes to 3. So we have these two cycles, these two loops if we wrap that around the cylinder. We can define the number of cycles in W and write that CYCW. And that'll be the number of loops that we get after wrapping the wiring diagram around a cylinder. And the sizes of those cycles are going to form a partition of n, because every one of the letters 1 through n is going to end up in a cycle. So the cycle sizes just have to add up to n. So I'll write C type to mean the cycle type of W to be the weakly decreasing sequence, i.e. partition, of cycle sizes. So let's do this for all the permutations in S3. So our permutations are 3, 2, 1, 3, 1, 2, 2, 1, 3, 2, 3, 1, 1, 3, 2, 1, 2, 3. And our cycle notation is, another way to do this without actually drawing the wiring diagram is to write two-line notation. Because the wiring diagram says that the letter 1 goes here, the letter 2 goes there, the letter 3 goes there. So 1 goes to 3, 3 goes to 1. and then 2 goes to itself. 1 goes to 3, 3 goes to 2, and 2 goes to 1. 1 goes to 2, 2 goes to 1, 3 goes to 3. 1 goes to 2, 2 goes to 3, 3 goes to 1, 1 goes to 1, 2 goes to 3, 3 goes to 2, 1 goes to 1, 2 goes to 2, 3 goes to 3. So the number of cycles in W is 2, 1, 2, 1, 2, 3, and the cycle type is 2, 1, 3, 2, 1, 3, 2, 1, and 1, 1, 1. Now we could count permutations that have k cycles, and we let little cnk be the number of permutations in Sn such that number of cycles is k. This is called the signless Stirling number of the first kind. Because the number Stirling was counting actually had a positive or a negative 1 associated to them. Now, an explicit formula exists for CNK, but it's kind of complicated. So let's just say it exists, and we won't have occasion to actually use it, so we won't worry about it. On the other hand, the number of permutations that have cycle type lambda is pretty easy. So let's write, it's easy, most easily stated, not in terms of lambda 1, lambda 2, lambda 3, which I guess we can write. So let's say this is the permutation which has k parts. If we say it has alpha 1 1s, alpha 2 2s, etc. up to alpha n n's, then the number that we're looking for, the number of permutations with cycle type lambda, is, well, maybe before I write down the formula, I should tell you how I'm going to think of it. So we could write, let's say we have a permutation of, let's say we're looking at n equals 8. So we can permute 1 through 8 in 8 factorial ways. And then if lambda equals 3, 2, 2, 1, we could break these into cycles by taking the first 3, the next 2, the next 2, and the last 1 to get a permutation having cycle type 3, 2, 2, 1. But of course that's overcounting, because 731, 317, and 137 are 3 different ways that the first 3 letters could occur and still give us that same cycle of size 3. Also, since we've got 2 cycles of size 2, they could happen in either order. So we're overcounting for 2 different reasons. So the formula is n factorial over So we can now look at the number. So this was multi-set notation, but we can look at the number 1 to the alpha 1, 2 to the alpha 2, 3 to the alpha 3, because we want to divide by cycle size, cycle size, cycle size, cycle size, because for every cycle of size k, or for every cycle of size p, there's p ways to write it. So if there's 3 cycles of size 4, we want to divide by 4 times 4 times 4. Or in other words, 4 to the third. So we want to divide by this because of the different ways to write each cycle. So the orderings of each cycle. And if there's no cycles of size n or no cycles of some other size, then our exponent is going to be 0, and then this integer to the 0th is just going to be 1, so we'll be dividing by 1. So it doesn't matter if these cycles don't actually occur. But then we need to think about how many ways are there to permute cycles that are the same size, that are going to give us the same permutation even though they look different using this method. So alpha 1 factorial, alpha 2 factorial, etc. up to alpha n factorial. And again, if any of these multiplicities is 0, say if n is not a cycle size, alpha n will be 0, and then alpha n factorial will be just 1. So this part is permutations of cycles of the same size. And the first part, I guess, could also be written as lambda 1 times lambda 2 up to lambda k, if we know how many parts there are. If we don't, we couldn't just write up to lambda n, because usually if we write lambda 1 through lambda n, we're saying, okay, some of those last parts might be 0, but we don't want to divide by 0 here, so we'd have to know exactly how many parts the partition has. So for n equals 8, so the number of permutations in S8 with cycle type 3221 is 8 factorial over 3 times 2 times 2 times 1 times 1 factorial times 2 factorial times 1 factorial, the multiplicities with which we see 1, 2, and 3. So 8 factorial over 3 times 2 times 2 times 2 times 8. So I guess if we wanted to simplify that, 7 factorial over 3. Now I think the main reason that cycle type is important is that conjugacy classes in the symmetric group are precisely the sets of permutations that have the same cycle type. So conjugacy classes in Sn are precisely the sets of permutations having the same cycle type. All right, so to prove this, first of all, we claim that the cycle type of W and the cycle type of SIWSI are the same for all I. So this will show that if any two permutations are conjugate, then they have to have the same cycle type, because one permutation is going to be the other times a product of generators on the right, and then the opposite product of generators on the left. So all conjugate permutations necessarily have the same cycle type. So to see this, let's consider the wiring diagrams of W and SIWSI. So W has a bunch of X's in here. And SIWSI has the same ones. So there should be the same number of wires on both sides. But we need the X in position between I and I plus 1 on the left and on the right for SIWSI. So we've got these extra X's here. All right, now when we wrap this, imagine wrapping both of these around a cylinder, and we'll look at the back side. So if we do that, we see well, if this backside is something like that, the other one is going to have, so I'll put the SI parts on the backside too. Now, this wire and that wire that weren't crossing on the backside here crossed twice there. So whatever cycle this wire belongs to, it's the same as the corresponding cycle that the corresponding wire on the other side belongs to. And whatever cycle this wire belongs to, it's just as big as its corresponding wire over here. So basically, if we know the cycle sizes, and we take two wires and we make them cross twice, we're not changing the cycle sizes at all. So that proves one direction. if two permutations are conjugate, then they have to have the same cycle size. All right, to prove the other direction, we have to look a little more closely at what this conjugation by SI does. We can do that with the wiring diagram also. So to see that permutations with the same cycle type are conjugate, we'll consider the effect that conjugation by SI has on the cycle notation. So maybe it'd be easier to have a sort of a general looking wiring diagram here. Something like this, and here's I and I plus 1, I and I plus 1, and then we've got this extra x there and an extra x here. So observe that I in SIW SI goes wherever I plus 1 was going to go. And that I plus 1 ends up going wherever I was going to go. And then furthermore, whatever was going to end up at position I now ends up at position I plus 1. So whatever letter that was going to end up at position I now ends up at position I plus 1. Similarly, whatever letter was going to end at position I plus 1 now ends at position I. The other wires that weren't going to end at or start at I or I plus 1 weren't going to end at I or I plus 1 don't change. So to summarize, the effect that conjugating by SI has on cycle notation is that it swaps the letter I and the letter I plus 1 wherever they are. So the cycle notation of SIWSI is just like that of W, but with the letters I and I plus 1 swapped. So that means if we have a cycle notation, something like A1 through A lambda 1, A lambda 1 plus 1 through A lambda 1 plus lambda 2, etc. We can conjugate by some sequence of generators. To obtain 1 through lambda 1, lambda 1 plus 1 through lambda 2, etc. So therefore our original permutation is going to be conjugate to this sort of most simple permutation of cycle type lambda 1, lambda 2, etc. So that means that every permutation of cycle type lambda is conjugate to the special one, 1 through lambda 1, lambda 1 plus 1 through lambda 2, lambda 1 plus lambda 2. And if they're all conjugate to this one, then they're all conjugate to each other. And that gives us the second part of the proof. So that means that the cycle type classes and the conjugacy classes are exactly the same. Now we said earlier that cycle type is not unique, and most of the time that's not a problem. We just write the cycles with whatever freedom we have, and we understand that there's equivalent ways to write them. But if we wanted to make it unique, we could come up with some conventions about which cycles have to come first and what letter has to come first in each cycle. So one way to do that is called standard cycle notation. So we define standard cycle notation by two rules. First, the largest letter in each cycle comes first. And two, we order the cycles in terms of increasing largest letter. So let's do this for S3. Alright, if these are the one-line notations, we've got 1 goes to 3, 2 goes to 2, 3 goes to 1, etc. So 1 goes to 3, 3 goes to 2, 2 goes to 2. 1 goes to 3, 3 goes to 2, 2 goes to 1. 1 goes to 2, 2 goes to 1, 3 goes to itself. 1 goes to 2, 2 goes to 3, 3 goes to 1. 1 goes to 1, 2 goes to 3, 1 goes to 1, 2 goes to 2, 3 goes to 3. Alright, now here we want to write 3 first because we write the largest letter in each cycle first. And then we write the cycles in order of increasing largest letter. So that means that this 2 will come first. So 2 and then 3, 1. Here, there's one cycle, so all we have to do is write the largest letter first. So 3, 2, 1. Here, we'll write 2 before 1, but 2 is less than 3, so 2 before 1 comes before that cycle having only 3. And here, write the largest letter first, so 3, 1, 2. 1, and then 3.